Okay, so last time we computed the cohomology of Rn, and it's based on the homotopy axiom because Rn has the same homotopy type as a point. Then the cohomology of Rn is just the cohomology of a point. Okay. Some students have asked me, why it's called an axiom when it's really a theorem. And it's because in the late 40s or the early 50s, in the last century, when algebraic topology was in its infancy, Eilenberg and MacLean, they single out a few basic properties of cohomology, and show that if any cohomology theory satisfies those properties, then they would agree, on all the spaces. Now, there are actually many cohomology theories. There's simplicial cohomology defined for simplicial complexes. There's singular cohomology defined for topological spaces and continuous maps. And what we're doing is de Rham cohomology. It's defined for manifolds and smooth maps. Okay. Now, all of these theories satisfy the axioms of Eilenberg-Stingrod, so that we know that they agree on, say, manifolds. Singular cohomology is more general because it's defined on topological spaces. But because singular cohomology satisfies the same axioms as de Rham cohomology, they agree on manifolds. Okay? So that's why the homotopy axiom is called an axiom. Okay? So today, I want to calculate the cohomology with compact support of Rn. Okay? So, lecture 7. Now, cohomology with compact support does not satisfy the homotopy axiom. So for example, we calculated the cohomology with compact support of R, and it's not the same as the cohomology with compact support of a point. Okay? So to calculate the cohomology with compact support Rn, we need a different method from last time. Okay? But I want to, kind of generalize a little bit what we did last time. So we start with a chart of a manifold. And then we define the projection map from U cross AB to U. Last time we just took the unit interval, but we can take the interval from A to B. Okay, and then we define the inclusion map going the other way. JT of X is XT. Okay? For T in AB. Um, then we can define integration along the fiber, okay? Because what we have here is a picture like this. So you have U cross AB, and we integrate along the fiber, we integrate out the T, okay? So I star, it goes from K forms on U cross AB to K minus 1 forms on U. And it's like last time, right? On type 1 forms, there's no T to integrate. So on type 1 forms, you just get 0. And then on type 2 forms, you have a dt, and you just integrate that out from A to B. Okay? So you get a function of x, and then you still have your dxj. I mean, this is exactly like what we did last time, except we have the interval AB instead of 0, 1. And then the proof last time will give us, you know, a similar formula. Last time I called pi lower star K because it was a co-chain homotopy, you know, between J1 star and J0 star, right? So we proved this formula last time. But instead of 0 and 1, you can have A and B. So we proved this. And this, where does it go? It goes from, now D increases the degree by 1, and pi lower star decreases the degree by 1. So you keep the degree the same. But when you do pi lower star, you get rid of the T component. Yeah, so this is where the maps go. So we still have this formula, okay? Now, okay, now can you replace this closed interval by the entire real line? Can you replace this closed interval by the entire real line? What do you think? Would there be any problem? Like, can I still define integration along the fiber, you know, by this formula and this formula? Like if it goes from minus infinity to infinity, Oh, good. Somebody's shaking her head. So why not? That's right. Yeah. Yeah. Um, you can't replace this closed interval by the entire real line because when you integrate over the entire real line, you might not get a finite integral, right? So this could be undefined. Uh-huh. But you can do that if your form has compact support. Okay? So if f has compact support, then you can integrate from minus infinity to infinity. Okay? And that's what we want to do today, right? We want to calculate cohomology with compact support. So we just want to look at forms with compact support. Now, a form with compact support is a form. So it can also be written as a linear combination of type 1 and type 2 forms. Okay? But the question is, do the coefficients have to have compact support? Um, because what you have is a sum, right? A form is a sum of terms like this, type 1 and type 2 forms. So if the sum has compact support, do the individual terms also have compact support? In general, it's not true, right? Because I mean, you can have, say, F looking like this, say. Uh-huh. So, and G looking like this, okay? So, I mean, F and G do not have compact support, but when you add them, you know, then the, 1 and minus 1 near infinity cancels out. And then, so F and G will look like this. So it has compact support. Okay, so it's possible for the sum to have compact support, but the individual terms do not have compact support. Uh-huh. And now we are looking at a form with compact support. It's a sum of type 1 and type 2 forms. Okay? So like in general, the individual terms need not have compact support. However, because the form is actually a linear combination of terms that are linearly independent, because all these dxi's are independent for I, like an increasing sequence of indices. Actually, it is true that when a form with compact support, then the individual terms have compact support. So I'm going to state that as a theorem. So here's an example where the sum has compact support, but the individual terms do not have compact support. But we have this theorem, okay, and that a form omega, which is the sum of AIX dxi, okay, where I runs over strictly increasing multi-indices, a form on a chart U x1 to xn has compact support if and only if the AIs all have compact support. Okay. Let me leave the proof as an exercise. I don't want to take up class time to do something like this. So I can give you a couple of hints. So first of all, the support has the property that the support of the sum is in the union of the supports. And then what's special about this particular linear combination is that the terms are linearly independent. And that means that if omega is 0, okay, so if this sum is 0, then because the terms are linearly independent, all the terms have to be 0, right? So all the, because the dxi's are linear independent, if the sum is 0, all the coefficients have to be 0. So using these two hints, you should be able to prove the theorem. I don't think this is in the book. Well, I am trying to write up some new versions, that would have this in it. Yeah. So eventually I'll post that on the internet. But yeah, try to prove this yourself. It's not that difficult, okay? And so now we can define integration along the fiber when the fiber is the entire real line. Okay. Yeah. So, well, it's actually the same definition. But now the functions will have compact support. So let's state it more formally. So we define pi lower star now for forms with compact support on U cross R to forms with compact support on U, okay, by on type 1 forms, pi lower star of f of x dxi is 0. And then on type 2 forms, it will just okay, good. Well, it'll be the same formula, but going from minus infinity to infinity, okay? So let me write it here. Okay. Now, why does this have compact support? Yeah. Okay. So because F has come, yeah. Oh, dear Jay, thank you very much. I really appreciate, you're pointing out little mistakes like that. Yeah. So since F has compact support, in U cross R, which is inside Rn cross R, you have a compact set inside a Euclidean space. So what can you say about that compact set? Yeah, in an Euclidean space, a compact set is closed and bounded. I mean, that's an equivalent condition. It's not true in general, in a metric space, but in a Euclidean space, that's true. So support of F is contained in a closed rectangle because it's closed and bounded. Okay, so you have a closed rectangle R inside U, and the support of F is in here. Okay. And so when you integrate along the fiber from minus infinity to infinity, it's the same as integrating from A to B, because the support of F is inside that closed rectangle. For some closed rectangle R inside U, and some closed interval AB. And so, let me see, yeah. Yeah, so the integral from minus infinity to infinity, it's the same as the integral from A to B. And well, so that's why it's defined. And then you can see that the support of the integral, which is a function of x, has to lie inside R. And support of the integral is in the closed rectangle. And this is a closed subset, and R is a closed rectangle, so it's a compact set. So you have a closed subset of a compact set, and so therefore, yeah, so this integral has compact support, in U. Okay, yeah. So let me see. Yeah, yeah, right. I'm looking for this. Yeah, so that's why I can say that I end up in this set of forms with compact support, okay, with degree 1 less. Okay. So now we have this. And so now let's look at what we proved last time tells us today. Now, um, uh, okay, let's go here. Okay, so um, so from last time, okay, no, from the generalization of last time. So we have for this new pi lower star, okay, d pi lower star plus pi lower star d is equal to, yeah, okay. Um, okay, for a particular f, right, it is the same as the integral from a to b. So if you apply it to a particular f, you will get JB star of f minus JA star of f. Okay. And can somebody tell me what this is? What JB star of this is? You pull it back. Well, like, in an exam, like if you are, asked to calculate an integral and you have no idea how to do it, and you just want to put down an answer, what answer would you put down? 0, right? Yeah, that works here because, this is going to be, so JB star of f, okay, and JB star commutes with D, so D JB star of T, and then which, so, well, okay, D JB star of DX, yeah. And, well, let's just look at one term, say, yeah, what is JB star of T? Or maybe let's look at JB star of F, okay? Now that's supposed to be a function on U. So it's a function of X. And, pulling back is the same as composition. And JB of X, that's the inclusion. And what is F of XB? If the support of F is inside this rectangle, 0. Yeah. Even if the support touches the boundary, it would still be 0. Yeah, because if it's positive here, it's going to be positive in the neighborhood by continuity. So the support will stick out. Okay? So if the support is contained in a closed rectangle, then at the boundary, it has to be 0. And so, yeah, so this term is, this term is 0. Okay? Yeah, so this is 0, so it's this. Okay? And so we actually have a theorem for this new integration along the fiber. We have d pi star is equal to minus pi star d. What conclusion can you draw from this? If I don't have this minus sign, what would you call that pi star? It's a, say it loud and clear. If pi star commutes with d, it is called what kind of map? It's called a co-chain map. Okay, because the differential forms form a co-chain complex with the exterior derivative. And here you have pi star, it's a map between two differential complexes. If it commutes with D, it's called a co-chain map. Okay? And the property of a co-chain map is that, complete the sentence. Why do you want a co-chain map? A co-chain map? That's right. A co-chain map induces a map in cohomology. Okay? Now, this says that pi lower star is a co-chain map up to a sign. The sign really doesn't matter. It's still, if it's a co-chain map, it still sends cycles to co-cycles and co-boundaries to co-boundaries. So it still induces a map in cohomology. Okay? So the conclusion is that pi lower star induces a linear map in cohomology. Yeah. So since pi low star is a co-chain map up to a sign, up to sign, it induces a linear map in cohomology. Okay, so that linear map I will call pi lower hatch, and it's going to go from the cohomology with compact support of U cross R to the cohomology with compact support of U in one dimension less. And the main theorem today is that it is an isomorphism. Okay? Is a linear isomorphism. Now, this theorem is also called the Poincare lemma. For compact support. Okay. And now let's see what implications it has. Okay. Okay. Now, I think if it's that low, people can see it online. So, so let's take U to be Rn minus 1. So let's look at an example. The cohomology with compact support of Rn in dimension n that you can write as cohomology with compact support of Rn minus 1 cross R. So take that to be U. And Poincare lemma says that this is isomorphic to the cohomology with compact support in dimension 1 less of Rn minus 1. And so you can continue. And then you see that you are going to end up with H1 with compact support of R. Okay. And that we already know, right? What is H1 with compact support of R? R, okay? And then now if you look at dimension less than n, HK with compact support of Rn would be, now each time you reduce the K by 1 and N by 1, so eventually you get K equal to 0, and then N is reduced by K. Okay? So for K less than N, this is R, R square, R cube, and so on. So this is not compact. The Euclidean space is never compact except for R0, right? R0 is just a point. So what is this? I think you did this in your homework. The cohomology with compact support in degree 0, that's represented by a function, a constant function with compact support. So on a non-compact set, yeah, a constant function, has non-compact support unless it is 0. So this is 0. Oh, yeah, this was a homework problem, right? Yeah, right. And so, yeah, so now we know the cohomology with compact support of Rn completely. Theorem. So we have the theorem. The cohomology with compact support of Rn is equal to R for K equal to N and is 0 in all other dimensions. Okay? Okay, now, so we want to prove the theorem, okay? That pi lower hatch is an isomorphism. Well, to prove that it's an isomorphism, you just have to find an inverse map. Okay? And it's kind of easy to see what the inverse of integration along the fiber should be. Okay? You're going to start with a form on U, and you should wedge it with a form on T whose integral is 1. So that then if you go this way, okay, you wedge it with the form in T whose integral is 1. And then when you do pi lower star, you know, that integral along the fiber gives you 1. So you end up with the original form. Okay? Yeah, so it's very easy to construct the inverse. Okay. Okay, so you want a form whose integral is 1. And so all you need like is a bump function, okay, rho of T, whose area under the graph is 1. Okay, so let rho of T be a C infinity function as shown with integral yeah, so the integral of rho of T, let's integrate it from minus infinity to T so that you have a function of T. Okay, so let's call this A of T. So this function is going to be 0, and then it will start increasing, and then it will give me the entire integral 1, you know, and then when I continue, I don't get any more stuff under the curve, so it will have a graph like this. Okay? That's the integral of rho of T. From minus infinity to T. But yeah, from minus infinity to infinity, it will be 1. And then you define E to be the one form, rho T dt. Okay? And this is a closed one form because, you know, when you take D, you get a 2 form on R. A 2 form on R is 0. So close because d of E is a 2 form on R. And then you just define an inverse to pi lower star to be a wedge product with E. So define E lower star to be E lower star of say f of x dx I to be wedging with E. Okay. And pardon? Oh, oh no, just a minute. Are you saying that I should change the name of the function f? No, this is rho. This is not f, sorry. Yeah, it's a Greek letter. Because the important thing is that this doesn't stick out, okay? Yeah, okay, good. Good idea. You know, you shouldn't have two symbols for the same symbol for two different things. Okay? But once you define that, then you can check very easily that pi star composed with E star is the identity, okay, on forms on U. Let's take a break for 10 minutes and then we'll continue. Okay, so let's continue. Yeah, so we defined an inverse map, which is wedging with the form in T whose integral is 1. And you see this has to be true because you start with a form in X, you wedge it with that form in T, and then you integrate out the form in T. So you'll end up with the original form. Okay? So I don't think I need to write down the proof. Yeah, so we found an inverse on the level of forms, but we want an inverse on the level of cohomology. And so we have to show that this E lower star induces a map in cohomology. And that means we need to show that it's a cochain map. Okay? It has to commute with D. And that is true. So here's the proposition that D E lower star is E lower star D, but again with a sign. Okay? And this would go from, let me see, omega k minus 1. Oh, this we want compact support, right? Yeah. D increases the degree by 1, and E increases the degree by 1. So actually, you increase the degree by 2. So let's check this. D E lower star of Okay, now instead of f of x dx, I'll just write eta. Simply because it looks cleaner. And by definition, this is E wedge eta. Okay? So, and then by the anti-derivation property of D, it's dE wedge eta minus E wedge d eta. Okay? But dE is 0, right? Because dE is a 2 form on R. So dE is 0. This is 0. And so you just get minus. Now, wedging with E, that's E lower star. You get minus E lower star of d eta. Okay, so that's the proof. And because E lower star commutes with D up to sign, it induces a linear map in cohomology. Okay? Yeah. Yes. Hmm? It's not on? Oh. So thank you for pointing that out. Hmm? It looks like it's on. Oh, I think where is the, the piece, the mouthpiece disappear. Oh, I see. So it's not connected. Oh no, it is connected. Oh, but you have trouble hearing in the back? Is it the position of the mouthpiece? Oh no, it's because I'm wearing a mask. It's not because the microphone is not on. It's because I was wearing a mask. So how's this? But thank you for pointing that out. All right. So let me see. So thus, E lower star induces a map in cohomology. Okay. So E lower star is going to go from the cohomology with compact support of U to the cohomology with compact support of U cross R, but in degree one more. This should be E lower hatch. Okay? Right now, we keep the map on forms distinct from the map in cohomology. It's less confusing, but eventually we use the same notation for both. Okay. Okay, and so we already have high star, lower star, E lower star is the identity on forms. Oh, and the induced map, how is it defined? Well, of course, it's defined in terms of E lower star, okay? And so if I lower star composed with E lower star is the identity, then I lower hatch composed with E lower hatch is gonna be the identity on the cohomology, right? Well, you know, like in group theory, I think you you know the theorem that, you know, if you have a homomorphism from a group to itself, and it's the uh, left inverse or the right inverse of something, then, well, let's say it's the right inverse of another map, then it will be the left inverse also, right? So in group theory, if you check that it's the inverse in one direction, you'll have the inverse in the other direction. But that's when the domain and the range are the same group. Now here we have two different groups, you know, so you can't just check one side, you have to check the other side also, okay? So you have to also check E lower star composed with high lower star. Okay? But if you check that, you find that it's not the identity. On the forms with compact support. But we don't actually need it to be the identity. We only need the induced map in cohomology to be the identity. Okay? And so the theorem is that there is a co-chain homotopy between these two maps. And you know that whenever you have a co-chain homotopy between two maps, they will induce the same map in cohomology. Okay? So what we need to find is a co-chain homotopy between these two maps. And let me show you how to find that co-chain homotopy. So between E lower star, I lower star, and the identity. Okay, so so K, you know, like it has to start with K forms with compact support of U cross R. Now a co-chain homotopy always lowers the degree by 1. And we are looking at the identity, so that means you're going from the same vector space to the same vector space. So we're going to define this K by, again, integration along the fiber. So on type 1 forms, k of f of xt dxi is, well, there's no dt to integrate, so this will be 0. And then on type 2 forms, you're going to integrate this f. However, you want to end up in u cross r, so you want to keep that t. Earlier, we wanted to end up with in u, so we didn't want the t, and we just integrated out. And so here, I'm going to integrate from minus infinity to t of f of u du. Okay? Because this way, you still have that t, but I think I should write it here. Let me see. So I integrate from minus infinity to t of f of xu du, and then dxi. Okay? Okay, now there is a problem with this definition. Can you see what the problem is? Yeah, this will not have compact support, right? Because if it's compact support, like this is compact support, but when you integrate to t, the resulting function doesn't have compact support. To have compact support, it has to be 0 at infinity. Okay? So in order to give this compact support, I should subtract the integral from minus infinity to infinity. Okay? Then at infinity, you'll get 0. But the problem with this formula is that now, now like, let me see. So yeah, so at minus infinity, right? If t is minus infinity, this is 0. But you have this term here that's non-zero. Okay. So this formula is 0 at infinity, but it's not 0 at minus infinity. And you need it to be 0 at infinity and minus infinity. Okay. How can you achieve that? Well, yeah, so the way to achieve that is that you multiply this by a function that is 1 at infinity and 0 at minus infinity. So that at minus infinity, this will disappear. And at infinity, you'll get this whole thing, So you need to subtract this, multiply by a function a of t, where where a of t is equal to 1 for t large and equal to 0 for t very negative. If you do that, yeah, then it will be 0 for t large and 0 for t very negative also, okay? So you want a function like that. Now, where is a function like that? It's right here. You can take a of t to be the integral of rho of u. It's right here. So we take a of t to be the integral from minus infinity to t of rho of u du. Uh-huh. Well, I didn't plan this, but it just ended up this way so perfectly. Uh-huh. And so that's our formula. And right, that's the only way to define integration along the fiber while preserving compactness. And it's kind of amazing. Well, it's a very natural definition, so maybe it's not so amazing, but it is, I think it is still amazing because, you know, you have to do quite a bit of calculation to show this. We have this theorem that dk plus kd is equal to 1 minus e lower star pi lower star. And, you know, this formula is different from the one in the book. The one in the book has a sign. And for 42 years, it bothered me that there was that sign there. But yesterday, I realized that if I define k differently, you know, by moving dt to the front instead of in the back, then there's no sign. I have to produce a new version, you know, of this section. I mean, the formula in the book is correct, but its definition of k is a little bit different, and you end up with a sign. Okay, now, there are certain things in mathematics that is best done in the privacy of your own home. And this proof is one of them, okay? I mean, it's not difficult, but it is long. And you have to make sure that you get every step right. You can try to do it yourself. If you don't succeed, you look at the book. The book has a proof, you know, for a slightly different formula, but it's the same idea, okay? So I'll just say do at home. Uh-huh. And so what this says is that thus in cohomology, because you have a co-chain homotopy, you get that the two induced maps in cohomology are equal. Okay, so this is now in cohomology HKC U plus R to HKC of U cross R. And so this proves that they are inverse to each other, right? Because we proved the other direction earlier. And so this completes the proof of the Poincare lemma. Right? And now, this can be generalized to pi from M cross R to R. Because you see, the integration along the fiber only involves t. It doesn't involve x. If you change to different coordinates, it's only the x coordinate that gets changed. So it really doesn't disturb integration along the fiber. It's like what we did last time, right? When we extended our pi lower star last time to from a chart to a manifold. So you do the same thing, and then you get this theorem that the cohomology with compact support of M cross R is isomorphic to the cohomology with compact support of M, but in degree 1 less. So I'll just say same as last time. To show that like integration along the fiber doesn't depend on the coordinates. Okay? Oh, so this should be pi lower hatch, right? Hmm? The line right above that. Oh, right. Okay. Well, again, I thank you very much for this. Yeah, I don't want it to be filmed with mistakes all over the place. Yeah. Okay, so we'll stop here today.